Thanks everyone for joining. And today we'll talk about how new techniques and technologies in the cloud specifically can help you to address the data integration and data silo problem. So agenda for the presentation will look something like this. We'll talk a little bit about the history of the data warehousing and data lakes, because those two evolved separately, and there's some different properties about each of those. And then we'll talk about how a new approach, specifically in the cloud, can look into combining both of the data lake and the warehouse in a unified data platform, and why would you want to consider doing that. And I'll follow up with the actual real case study from one of our customers where we successfully implemented a platform following those principles. So it's only 30 minutes long. I think it's packed with details, so we'll try to go fast. And this, all right, this doesn't work for some reason. And my presentation just fell asleep. All right. My name is Danil Zburivsky. I'm a cloud data platform architect at Pythian. So I usually spend my days helping customers with their data problems and helping them design and architecting data platforms. I live in Halifax, Canada, and that's the east coast of Canada. And if I don't work or write technical books, I surf. And yes, people surf in Halifax, and yes, they do surf all year round. You can't really see, but there's maybe 5 or 6 people in the water on that picture. Yeah, it's rough, but the waves are really good. So I also write technical books. I wrote a book called Hadoop Cluster Deployment. Don't buy that one. It's outdated, and I don't recommend it anymore. So don't do that. My colleague and myself, Linda's over there. Linda, wave a hand. We are actually working on another book right now, which I do recommend, and it's called Designing Cloud Data Platforms. The only little problem with that one is it's not ready yet, so we're still writing it. But keep an eye on the Manning. We're working with Manning on this book, and keep an eye on Manning website. We should have the book in the early access program, first several chapters, I think in the next several weeks. And the book should be released later this year. So a lot of things that I'll be talking about today, they will be covered in way more details in the book itself. So as I said, I work for Pythian, and what we do for at Pythian is we're helping businesses to transform and win in data economy. So we try and help companies with all the aspects of their data journey, from the operational databases to machine learning and analytics, both on-premise and in the cloud. So we have a booth here, so if you're interested to talk more about after the presentation, please stop by. So it's been mentioned several times today, and at the keynote as well, that ETL is not, integration of data is not a new problem, and it's been around for a long time. But why? So why is data integration so hard? What is the thing about ETL that hasn't been solved yet? Any ideas in the room? What's the hard stuff about ETL? No? Yes?
Disambiguation of data, Salesforce calls it custom
Yeah.
thing.
Yeah, master data management is a big area of ETL. So the data itself, the nature of data itself makes it hard, but also things that Michael talked about in his keynote today, especially these things are more kind of challenging today, right? So I think he's talked about 3 V's, but I think we can actually talk about several things. The data volume itself, that's something that kind of has significantly increased in the last several years. And at the keynote today, I think Michael said that this is a solved problem. You just buy a Teradata, you just buy an Atiza, and they do this massive parallel processing, this is a done deal. But guess which service is most in demand at Pythian today? Migration from Teradata, migrations from Atiza. So people actually, yes, you can solve this problem. You can buy a really expensive appliance, but the thing is the costs, the support cost, the maintenance cost of the systems is too much for many organizations. People just can't afford it anymore. And there are more accessible offerings today that you can look into. Variety, that's the 800-pound gorilla in the room. Like, I think variety is really one of the key driving factors behind the challenges in ETL. ETL tools just have to be able to deal with different file formats, different sources, and they really have a hard time keeping up. And I'll show some examples later about what that means in practice. Velocity, data moves, some of the data and use cases around the data just needs to be processed in real time. That just, that's where the business is going to. And the last V, which I think it's often overlooked, but I like when people mention it, it's the veracity of data. When I bring all the data sources, which ones are actually one that I can trust? Like what actually, what's a high quality data? What's the data I can build my financial reports on versus what's like the temporary sandbox area for my data scientists to play with, right? So this is another big challenge with the ETL that we see. So if we look at the traditional data warehouse design and ETL process, I mean, it on a high level looks something like this. You have a ETL tool sitting in front of the warehouse, and the warehouse is responsible for everything. It's responsible for your storage, it's responsible for your data processing, and it's your SQL engine that does both the processing and the ad hoc queries that your analysts run, right? So, and a lot of problems that we see actually in ETL today, they arise from this model where everything is bundled to a single warehouse. And specifically, if you think about it, warehouses, like traditional relational warehouses, they usually bundle the storage and compute together. So you have your warehouse machine, it has some local storage, or it can have a network attached storage array or something like that. But the challenge is, like, if you want more capacity, for example, if you're on Teradata, you still have to buy more boxes, no matter whether you just want to have more storage or you just want to have more compute. And those things are usually need to be scaled independently. Some use cases just require a lot of storage, but they require very little compute power. Some of them, like machine learning, can be the other way around. They may require little storage, but they may require a lot of compute. Finally, when it comes to the data variety, since warehouses really use SQL as its processing engine, like all they can understand is SQL, and ETL tools kind of usually try to push all the workload inside the warehouse. Like SQL becomes this language that you have to choose. Like it's a great language for data access, but it's not a really good programming language. Like it's not a general purpose programming language. It lacks a lot of the things that software engineers today take for granted, like testing, abstractions, libraries, modules, like all these things that are common in software development world, they just don't exist in SQL, making SQL-based ETL brittle. Like it's really hard to design a really good pipeline using just SQL. Though again, I'm a SQL fan. As an access language for data, it's great. But as the general purpose language, I don't think it's good enough. And finally, a lot of the systems have been designed for batch processing, right? Like take your nightly data, load it into some staged tables, do some business logic on your ETL tool, and load the data into your fact and dimension tables. So the whole system is designed around batch processing. So when it comes to processing data as it comes in, like in real time, these systems are not specifically good at this. And finally, if I'm building a system where I can allow people to bring in data sources that they like, how do I solve the data quality problem? Like a very common scenario is for data scientists just to bring some data in to play with, to try their models on. And if they don't really follow any data management process, then it's really hard to tell which data is high quality, which data is low quality. So data veracity is a big problem. One of the key issues our customers always ask is, like, we have all this data, we have no idea which one is actually good and which one is not. So really, to summarize the challenges with ETL and the traditional data warehousing model, you can think about is that a lot of these issues arise from the fact that warehouses have this monolithic design. And monolithic design has all these issues that are associated with this. It's lack of flexibility, lack of agility. It's really hard to change things. And it's becomes, since resources are finite, like you have this big box of Oracle or SQL Server or whatever you use for your traditional warehouse, and it does all the nightly processing, heavy lifting to get your reports delivered to execs every morning, it becomes a really guarded resource because you just can't allow it to fail. You can't allow any extra load on it because then your reports are late and everyone is really freaking out in the morning. So it becomes a problem for people to do self-service. It becomes a problem for experimentation, and then kills the agility that everyone's looking for today. If you have been paying attention to the big data space, you may ask, okay, looks like we've been here at this point like 6 years ago, and wasn't Hadoop here to solve all these issues? Like, wasn't big like data lakes as opposed to the data warehouses? Isn't this the answer? Like, data lakes allow us to scale things on demand. They provide schema on read properties, meaning you can bring data from different formats and process it later. Like, all these nice features, like why are we still talking about like data lakes versus the data warehouse? Well, the problem is that I think Hadoop hasn't quite played out as the unified data platform. And the reasons behind this, as we see it at Pythian and in general in the industry, is that it turned out to be quite complex to use and navigate, use and operate. Like, it's a big system with many moving pieces, and just the operations aspect of it took quite a bit of effort. You have to basically have people dedicated, especially if you are working at large scales. Nodes will fail, you will need to fix them, you will need to keep the services updated, things like that. So it's hard, it's complex and hard to use. The promise of, okay, you have a Hadoop which scales by adding more servers into it. Like, the whole idea that you scale by buying servers, it may work easily for companies that have a buy new server process kind of nailed down. Like, if you're a Google scale or Yahoo scale, yeah, you constantly buy new servers. What we've seen in the reality, buying a server in an average company takes months of procurement time. So the idea that I will just buy servers and plug them in a month or in 2-3 months, caused a lot of the Hadoop clusters that I've seen in the past, they are either dramatically underutilized, so you buy more capacity that you actually need, or they're dramatically overutilized because you can't scale them fast enough, because buying stuff is a kind of a real world process. You can only do it this fast. So basically, these factors together killed the Hadoop cost proposition. Hadoop was supposed to be cheaper than traditional warehouse and more scalable. Well, it turned out to be, in some cases, even more expensive than a traditional system and more complex to manage because you had to have all the new set of skills. So what we need today is we need a modern data platform that follows a different design principle. So we talked about the monolithic design of a traditional warehouse. Hadoop kind of moved in that direction, but didn't quite get there. So what we mean by modular design is we mean that different functionality of the data platform are represented by layers that are loosely coupled with each other. So loosely coupled means I can swap one layer for another with a similar functionality without having to rewrite my whole system. So for example, storage has just to store data. It doesn't need to do any compute power. It doesn't need to do any compute associated with it at all. Ingestion just needs to move data from sources into the storage without as little processing as it can. Then you have the processing layer, which needs to operate on this data and storage at scale. And then you build on top of this your analytics and data access layer. And processing layer will implement all the business logic, QA rules, and things like that. So that's what we actually need as the design and guiding principles for our data platforms. So, like, the modular design sounds great, but to implement it in practice, we need cloud. Really, I don't think we have any other options to implement have a practical implementation of these ideas other than in a public cloud. And the reasons for that is that the public clouds today basically are comprised of a number of services that can be stitched together in different ways. So they kind of already been built for this modular design. Like, you have your storage services, you have your processing services, you have your database services. So these things actually work together very well. Cloud is elastic, both in performance and price. So you only usually pay for what you use. You can get storage instantly, and you can get compute almost instantly without waiting for months for procurement. So this feature is really important for the scalability properties. And a lot of the services, especially in data space, across the three major cloud providers like Amazon, Google, and Microsoft, a lot of the data services that they have are platform as a services, meaning they are managed. Like you don't have to spend a lot of our time on operations side of the things. So combined all these properties in the cloud, I think allow us to actually talk about a practical implementation of a data platform. And finally, I think we need to kind of put to rest the debate between like a data lake and a data warehouse, because they both have their pros and cons. Data lake is flexible. You can bring different data sources. You can delay managing, like processing schemas in the lake after you have already ingested the data. Warehouses are really good at the structured, curated data sets. They're really fast for the relational type operations. So I think really what we need to do is we need to combine them both. So that's, I guess, the key idea behind the cloud data platform is that it's a combination of a data lake and a data warehouse. And since the design is pluggable, then you have different options on how you combine those things together. So this is a diagram that represents all different components that you can have in the cloud data platform. And there's a lot of going on, and I'll quickly walk through each of those layers. But I want to mention right away that the important bit about this design is you don't need to implement it all. Like the pluggable architecture means that you may skip some of the layers. Like for example, if you don't need real-time analytics, you can skip the whole fast storage real-time aspect of it and add it later. So design doesn't prevent, like it doesn't force you to make a decision today on how your system should look like and invest into specific technology with kind of anticipation of use cases. You can always add things later if you follow the design principle where things can be actually composed together from different blocks. So going through the diagram here real quick. So we have the ingestion layer, which is both supporting batch and streaming, just delivering data. The key idea here is we need to ingest data with as little changes to the data itself as possible. Like we're not doing ETL and ingest. Like that's one of the key design principles. Just ingest raw data, save it in either to the slow storage for permanent kind of retention for batch use cases, or to the fast storage for real-time analytics, and don't do a lot of modifications to the data itself. When it comes to storage itself, I kind of use terms slow and fast storage just to kind of separate those, but usually it's represented, especially in the cloud, by slow storages in object store like Amazon S3 or Google Cloud Storage or Azure Blob Storage, things like that. And fast storage are messaging systems designed for basically processing data that comes message after message in real time. So Kafka is a good example of fast storage, Google PubSub, AWS Kinesis, things like that. So this is two systems that are kind of serve the different purposes, right? So batch data and archive data and raw data will go into the slow storage, and the messages as they come in, they go to the fast storage, and that's how these things can kind of coexist in the same architecture. When it comes to processing, the distributed framework is critical. So you need to have a processing framework that can scale. So a good example of that is Apache Spark as one of the frameworks that we have successfully used in the past. There are others. There are some like Apache Beam that combine the real-time and batch processing in one, though I find it a little bit more kind of complicated and less mature than Spark at this point. But the idea is if you're doing real-time and batch, today most likely you will end up with two processing frameworks that you will have to learn and your team will have to use. There's some unification going on that front, but I don't think it has happened yet. Finally, your warehouse becomes a destination and just one of the components in the whole design. So the warehouse essentially accepts the curated and prepared data sets that have been already cleaned and processed and managed by the processing layer here. And really, if you think about the purpose of the warehouse is to serve queries to the end user as fast as possible. Like it's not supposed to do the ETL. It's not supposed to do large-scale data transformation. Its sole purpose is to solve queries and then serve queries to the end users. And in this design, I think that's highlighted that the data processing happens outside of the warehouse, and the data consumers actually access it just for the query and ad hoc analytics and schedule reports and things like that. But as been mentioned, I think today already several times, not everyone from the data, the number of different data consumers today is way more diverse, and the types of them is way more diverse than probably what we have seen several years ago. So not everyone is happy from a data consumer perspective with the SQL-based curated data sets. If you're talking about machine learning applications or data mining applications, many people or tools prefer to actually use data directly from the raw storage. So, and this design actually allows you to do that without any significant modification, because the data flows through the ingestion stream and it goes into the slow storage. And there are a number of tools in the cloud that allow you to run queries or run processing directly on the files without even touching the warehouse. So that's a really significant shift, because really that's what we've been trying. When you're dealing with relational databases, you're always thinking about, oh, okay, I need to normalize my data so I don't just store duplicates. Like, this is a different concept. You have the really low-cost storage and really accessible compute, so you can afford the duplication of data. You can store the same data here and there in different formats just to serve the data consumers, because that's the whole idea behind the data platform. It needs to serve the community of the data consumers. Finally, what I wanted to mention is the automation is really important, because again, many different services, they need to interact with each other, they need to work coherently. So your pipelines will require some kind of metadata store. And here, metadata, I'm not actually talking about business metadata. That's a separate topic. They're usually additional tools that you can get to manage your business, like data catalogs and things like that. Here, I'm talking about the technical metadata for pipelines, like which pipelines ran, how many rows they processed, what did they do, were there any errors, did they pass QA checks, like a lot of information that pipeline needs to capture. You need to have some kind of repository for this data for reporting, for monitoring, and for automation, the most important bit. An important part of this design is that there is kind of a set of new tools in the cloud, and I'll talk a little bit about specifics when we actually do the case study. But there's a new family of the ETL tools today in the cloud that kind of provide this overlay for managing data. And usually the ETL tools, and there's some from Google, some from Microsoft, and from Amazon, they usually include some kind of metadata repository in them. So that's why I highlighted them both. Sometimes, and we've done it for other customers, we actually have a dedicated repository specifically for pipeline automation. But sometimes, if the use case is simple enough, you may be just good with the whatever ETL tool provides you with. We'll talk about data consumers as well, but again, different consumers require different data. Some people go directly, or people or applications like Tableau or dashboarding tools go directly to the warehouse. Real-time analytics usually requires way faster response times than what warehouses can provide. So for that, you would usually use either an in-memory cache or some key value store to front the data. And usually the data consumers for real-time are not people. People don't, like the speed at which the real-time happens is not something that humans are monitoring and making decisions. It's usually other systems, other applications. And finally, through direct data access, machine learning applications and data mining applications can go directly to the storage for that. So what I'd like to do now, we have 5 minutes left about. I'd like to, this looks great in theory, like this design, it's pluggable, it's flexible, you can do this, you can do that, but actually have we done this in a real scenario? And can we show some of the results of the practical implementation of that? Yes, we have done it for many customers. I'll talk about one of them on GCP. It's a luxury fashion brand from Europe. It's been around for quite some time. And surprisingly, they have a data integration problem. They have data all over the place, and they need to answer the questions that they can't because the data is separate. So the way things looked for them really kind of high level before we started talking about the cloud data platform is they had some retail transactional data in their Oracle databases, like there's a number of them. They have some inventory data coming in flat CSV files through FTP servers, been doing this for some time. And there's web analytics data coming from Google Analytics. So before we started, like they obviously were doing analytics before we came to them. Like they've been around for a while, they've been very successful, so they must be doing some business analytics. Like, can anyone guess what they had in the middle? Like what was this question mark? Where did they bring the data in to do analytics? Any? Excel, yes, this is what it was. They were doing it in Excel, and this is very common because many people actually said Excel right away. And it was hard because it was a manual process. Like people every month, they had these monthly dashboards, and every month they had to bring data in manually from all these data sources, massage it some way in Excel, and they had dashboards that look something like this, and this is a simple one, and they have dozens of them, and they do it every month, and they do it over and over and over again. So you can imagine that the amount of manual effort going into this is just mind-boggling. And the amount of errors people can make while manually transferring data is also astonishing. So it's not only the automation problem, it's also a data quality problem in some sense, because people make mistakes while entering data like this all the time. So really, what I'd like to highlight is that this case study didn't really have a volume problem. Their data volume was small. Like they didn't really have petabytes or even terabytes of data. We're talking about gigabytes of data. It's quite small. But they did have the variety problem. They have different data sources. They definitely had a data quality problem, so they needed to assure that some of the data coming in from files had all the kind of business rules checked in and things like that. And they had a self-service problem because obviously this spreadsheet is static and you can't really do any, like you only look at the analytics as it was presented to you. You can't really do any ad hoc queries against it or anything like that. So really, I guess the key message that I'd like to, one of the key messages I'd like to reiterate, like you don't really need to have a big data problem to benefit from having a data platform like this. For example, like here I highlighted some of the areas and like layers in the data platform and specific Google, like this is a GCP implementation that was implemented on Google Cloud Platform. And I highlighted some of the actual services that we've used for this implementation. You can see that we actually didn't do any real time. The dashboard, like we actually talked to the customer and they said, yeah, oh yeah, we do want real time. But the dashboard, which was the most, like the biggest pain point was monthly, right? So like there's no need for real time. Like we can add real time later, but in this case we didn't do it. So we didn't really try to over-engineer a complex solution for them where they didn't need it. So for batch, like it was all batch data using a new service from Google Data Fusion as an ETL overlay, ingesting data into the Google Cloud Storage as the permanent file storage. BigQuery becomes our warehouse. And for the data processing, we're using Apache Spark running on Dataproc, which is a managed cluster from on GCP. And the beauty of it is it's managed. Like I don't need to deal with the like upgrading and installing software. I just run my jobs on the cluster. Another important point about running processing using tools like Dataproc is I only run the job and I only have the cluster available to me only for the duration of the job. And it's usually like several hours and months. So I don't really need a permanent cluster sitting there all the time when I don't need it. Like this is the elasticity of the cloud that I was talking about. Things only exist and you only pay for them while, when you need it. And BigQuery as the cloud warehouse is following the same model in terms of pricing. You only pay for the amount of queries you run. So if you only do processing heavily once a month and the rest of the months it's idle, you're actually paying very little for the resources. And in terms of the data consumers, it was mostly the Tableau dashboards connecting to the BigQuery to get the data, and the machine learning and data mining applications going directly into the storage to process the raw data. So we had the raw files available. We're running out of time, so I quickly will skip through some of the things. I wanted to show you the variety problem here. Like this is, I'm not sure if you can read it, but this is how Google Analytics data looks like if you work with Google Analytics. if you've been doing any BI or relational kind of data modeling, you can see that it's really terrible. It basically separates the column headers from the data itself. Like the data itself is nameless. Like looking at the data set, data part, I can't really tell what those metrics are. I need to find them in the column header section of this data. So it may make sense for the developer who developed the API, like it doesn't make any sense from an analytics perspective. So you need to write some processing that will actually unwrap this column, like this is JSON structure, right? So you unwrap this JSON structure in a flat table. And Spark is really good at it. So I just didn't want, I wanted to show you some Spark. Don't have time for this, but it's not scary. Reading a file from Google Cloud Storage and running queries on the file in Spark takes you about 5 lines of code. Like it's not MapReduce. Spark is pretty mature at this point and pretty accessible. Data quality, real quick, the fact that we are now in cloud and we have the scalable storage and scalable compute available to us allows us to arrange data and storage in tiers. So you can have a raw tier where you store data which hasn't been checked for anything. And then you can have tiers, which basically folders in the cloud storage, really, if you think about it, that have been processed and apply data quality rules. So you have like a raw folder, and then you have clean data folder, which only contains data that passed the checks. So that gives you the foundation for the whole kind of company and the whole data consumers community to work with the clean data if they want to, and only go to raw data if there's absolutely need for that. Like these are the rules that are business-wide. But then when you're producing actual reports, you may have data validation rules that are specific to those reports and nothing else, right? So you only apply a subset of the validation rules that are only specific for a specific data product. And the fact that we now can run multiple jobs, we can have multiple clusters, we can apply as many rules as we want, it allows us to create this flexible data quality control mechanism. Data fusion from GCP, as I said, and a UTL tool. If you don't have any engineers on staff or prefer visual kind of ETL tools, this allows you to basically build jobs and it writes Spark code for you. So that's a benefit in terms of boosting productivity for engineers. Scheduler, we used GCP Cloud Composer, which is based on open source Airflow. Airflow is great, check it out. It's a great and powerful orchestration tool. So I know I need to wrap up now, but really, what this customer is able to do today that, well, first of all, they don't have to maintain the Excel spreadsheet anymore, which is great. But they now can add new data sources in a self-service mode. They can do self-service analytics through Tableau, which is a way more powerful tool than Excel for this needs. They can implement their own transformations using the data fusion, and they are not Spark programmers, so they prefer to do that. And they have a data quality process in place that allows them to have this multi-tiered data organization in the cloud storage with different levels of data quality in those tiers. With that, thank you very much. If you have more questions, either find me after the presentation or stop by our booth in the expo hall. Thank you.